So on to objective 4. We want to convert from degrees to radians and from radians to degrees. So since we have two ways to measure angles, we have to be able to convert them. So we need to be able to convert degrees to radians. Say if we want to find arc length, but theta is only given in degrees, we would need to put theta in radians. So we can find this conversion by using the circumference of a circle, which is 2 pi times the radius. If we replace 2 pi r with s in our arc length for the equation, we can end up getting s is equal to r times theta, where we've replaced s with the circumference of the circle, 2 pi r, is equal to r times theta. Then we can cancel out our r's, and we end up getting that theta is equal to 2 pi radians. So our radians is most often measured in pi, terms of pi. So 1 revolution around a circle is 2 pi radians. So now we can use this since we know that 1 revolution in degrees is 360 degrees. So this means that 360 degrees is equal to 2 pi radians, and we're often going to see that radians will be abbreviated to rad. So that's what that means, so 2 pi rad or radians, which we can then just divide each side by 2 to end up getting that 180 degrees is equal to pi radians. So then our conversion formulas are going to be that 1 degree is equal to pi divided by 180 radians, or 1 radian is equal to 180 degrees divided by pi. So here's a table of the radian and degree measurements of common angles. So these are just going to be really common angles. We're mostly just saying here that it's in increments of 15 degrees. And then these are all the radians that correspond. So for example 3, we want to convert some angles from radians to degrees or degrees to radians. Now, we can pretty easily figure out what it is by looking at the table, but let's go ahead and actually do it by converting using our formula. So for part A, we're converting from radians to degrees. If we're converting from radians to degrees, this means that we're going to be multiplying by 180 divided by pi to get our answer in degrees. So we have negative 7 pi over 4, which we're now multiplying by 180 divided by pi, where 80 is in degrees. We see that our pi's will cancel out. We can also simplify our 180 and 4 a little bit. We can divide each side by 2. So we can get 90 and 2. So now we'll end up with negative 7 times 90 divided by 2, where that's in degrees. And if we simplify this, we get negative 630 divided by 2, which simplifies to negative 315 degrees. Where now, if we actually look at the table, 7 pi divided by 4 corresponds to 315 degrees. We see right here. And if it's negative, that just means our degrees are negative. So we can use the table fairly easily if we're able to, but if we're not able to, then we want to use our formulas. So part B, we're converting the angle from degrees to radians now. So going from degrees to radians, we're now going to be multiplying by pi over 180 to get our answer in radians. So we're taking 150 degrees divided by nothing, and we're multiplying by pi divided by 180 degrees, and pi is in radians. So we can simplify it quite a bit. 150 and 180 are both going to be divisible by 30. So if we divide each side by 30, then this is going to end up giving us 5 and 6. So this is going to end up giving us 5 pi divided by 6 radians, which then we can go ahead and confirm in our table. So we see 150 degrees is 5 pi divided by 6. So we know our answer there is correct. So all right. Moving on to objective 5, we want to find the area of a sector of a circle. So now we're finding the area of a chunk out of our circle. So from figure 15, which we're looking at here, the ratio of theta and theta 1 is equal to the ratio of A and A1, areas of red and blue sectors. So theta 1 and A1 are red, theta and A are blue. We then let theta 1 be equal to 2 pi radians and A1 be equal to the area of a circle, which is equal to pi r squared. Then if we solve for A, we're now going to get the equation for the area of a circle. So the area of the sector of a circle of radius r formed by a central angle of theta radians is A is equal to 1/2 r squared times theta. So the equation is the most important part. Everything we just went over is just leading up to how we got to the equation. So the equation for the area of a sector is area is equal to 1/2 radius squared times our angle theta. Let's go ahead and use it in a problem. So example 4, we want to find the area of the sector of a circle of radius 6 feet formed by an angle of 45 degrees. Then we're going to round to 2 decimal places. So if we want to find the area of the sector, we want to use the equation. So we know the equation is area of the sector is equal to 1/2 radius squared times theta. So we're trying to find the area, but what we have here is that our radius is 6 feet and theta is 45 degrees. So we have that theta is 45 degrees, but we need radians. We need to have our answer in radians because we're using this area of the sector. Whenever we're finding the area of a sector or arc length, we have to have theta in radians. So theta must be in radians, which means that we need to convert it. Let's go ahead. We'll just look at our table. 45 degrees is a pretty basic angle, so it's definitely going to be in our table here, where if we look, 45 degrees corresponds to pi over 4 radians. So this is equal to pi over 4 radians, and now we can just go ahead and find our answer. So we have our area, which is A, is equal to 1/2 times radius squared, where our radius is 6 feet, times pi over 4. 6 squared is going to be 36. So we have 1/2 times 36 times pi over 4. We'll go ahead and do 36 times 1/2. This will be 18 times pi over 4, which we can actually just write as 18 pi over 4. 18 and 4 can both be divisible by 2, which leaves us with 9 pi divided by 2. So we have our area is 9 pi divided by 2, but we want our, oops, sorry. My screen kind of wigs out from time to time. So it just did that. But anyways, so we have our area in 9 pi divided by 2, but we want our answer to be in feet, and we want to round to 2 decimal places. So we need to convert 9 pi divided by 2. This is where having a calculator comes in handy. So when we have a calculator, we can easily plug in our calculator, 9 times pi, find that answer, divided by 2. Or we can use an online calculator like Desmos. So whether you're using a handheld calculator or Desmos, when we plug this into our calculator, this answer is going to give us, rounded to 2 decimal places, about 14.14, and this is going to be in square feet since we squared our radius. So this is square feet. So we always have to look out for that when doing problems on MyMathLab, because if you enter in your answer in radians, it will then technically be counted wrong. So you'll have to enter it whenever it wants to round to 2 decimal places or round to a certain amount of decimal places. It wants you to put it back into the original units that you had and then go ahead and round. All right. Last objective, objective 6, we're going to find the linear speed of an object traveling in circular motion. So for motion along a circle, we distinguish between linear speed and angular speed. So linear speed, we suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on the circle, then the linear speed v of the object is defined as v is equal to s divided by t. So the important part of this question, linear speed has an equation of v is equal to s divided by t. So s, distance traveled in time. So distance divided by time. So as this object travels on the circle, we suppose that theta in radians, so in radians is the important part, is the central angle swept out in time t. So in our angular speed, we say the angular speed omega, which we're saying is the Greek lowercase letter omega, of an object is the angle theta, measured in radians, swept out divided by the elapsed time t. Or just that omega, which is our angular speed, is calculated in theta divided by time. So if we were to be spinning a ball on a string and we're spinning it around, it has angular speed. The moment we let go, it has linear speed. So there is a relationship. The relationship between linear and angular speed is that linear speed is equal to v, which is equal to s divided by t. So that's by equation 9, or by the equation of linear speed, which we can then replace s with r times theta, that was our arc length. So r times theta divided by t, where we then say that r times theta divided by t, where theta divided by t is the angular speed omega. So we have that relationship between them. So therefore, linear speed can be found by multiplying the radius by the angular speed. So omega is measured in radians per unit time. Your radius is measured in how many units you have. And then you have your linear speed. So our final equation, which is the most important equation now, is going to be that linear speed is equal to radius times angular speed. And we'll go ahead and use that in our last problem here. So for example 5, a child is spinning a rock at the end of a 3-foot rope at the rate of 200 revolutions per minute, which we call RPM. Find the linear speed of the rock when it is released. And then we're going to round to 2 decimal places. So we have our radius. It's 3 feet. But we need to find omega. And omega is found in radians. But we're given revolutions. Well, if we remember, 2 pi radians is 1 revolution. So we need to change revolutions per minute into radians per minute instead. And we're going to use our equation here for linear speed because we're finding linear speed here in the end. So to start off our problem, we have that radius is equal to 3 feet. Our angular speed, which is identified by spinning a rock at the rate of 200 revolutions per minute. This is our angular speed. So this is omega. And omega is 200 revolutions per minute. But remember, we want this in radians. So if we have 200 revolutions per minute, we know that 1 revolution is the same as 2 pi. So 2 pi radians is the same thing as 1 revolution. So this is now going to simplify to 400 pi radians per minute. So now we have the same, we have the right units of time for our angular speed, since we said that omega is measured in radians per unit time. So now I have the right radius, and we have the right omega. And we want to find linear speed. We know that linear speed is found by multiplying the radius and omega. So let's go ahead and multiply them. So our linear speed V is going to be equal to 3 times 400 pi, let's write this, 400 pi radians per minute. 3 times 400 is going to be 1200. So we have 1200 pi radians per minute. And since we just multiplied our radians times our radius, so we had our theta times radius, this is actually going to turn into feet per minute now. Our radians get overtaken by whatever unit that we had of measurement for our radius. So this is now 1200 pi feet per minute. And we want to find the, actual value. We don't really want our answer to be in terms of pi. So we're going to use a calculator, and we multiply 1200 times pi. This is going to end up giving us 3,770 feet per minute. Feet per minute is a little bit of an odd measurement. We really like to have it in miles per hour. It doesn't tell us in our question to convert to miles per hour or anything like that, but in my math lab, it would tell you have your answer in whatever unit. So if it said that feet per minute was fine, you could definitely leave it like this. Or converting this into miles per hour, this would turn into about 42.8 miles per hour. So any one of these would be correct. But remember, since it asked you to round to 2 decimal places, that you want to have these values instead. So rounding to 2 decimal places, these were the final answers there. So, all right. That concludes our lecture here for section 6.1. So if you have any questions on anything that we went over, please use the question form, or you can go ahead, email me directly, or stop by office hours. So all right, I'll see you all again in section 6.2. Have a great day, everyone.